Hey, Mr. Sims.
Yeah.
Hey, we're starting Unit 8 today.
Giddy up.
Giddy it up. The atoms and bonding. We're about bonding.
We are. No, we've talked a little bit about atoms, and we've talked about some of these characters back in Unit 1 or 2 or something like that.
Yeah.
But we're going to go into a little bit more detail, talk to you about the history of history of how we got to what we know about the atom.
Okay, cool.
So, because we didn't always just know.
Yeah.
It took us a while.
Well, atoms are kind of small things.
They're very small.
Remember how small atoms are? How big are atoms?
Tiny.
Tiny.
So if we blow up an orange to the size of the Earth, the atoms are the size of cherries.
That is correct.
What we talked about. Yeah.
So yeah, you take the orange and you blow it up to the size of the Earth, and the atoms are cherries. Wow, that's a lot of.
That's a lot.
That's a lot of cherries.
It is.
That means they're really tiny.
Really tiny.
Wow. Okay, so this is podcast 811, folks, the history of the atomic theory.
Yep.
All right, hey, history of the atom. The first guy we want to introduce to is Mr. John Dalton.
Now, this is the first modern person.
That's
I think
true.
back in, did we talk about Aristotle and Democritus back in the other unit? Yeah, so there's this guy named Democritus. He was a Greek, and he said, hey, there's these things called atoms, and then Aristotle said no, and Aristotle everyone's heard of, and no one's heard of Democritus. That's because Aristotle won the argument back in about 400 or 500 BC, I think. So, yeah, Democritus said there are atoms. Aristotle didn't. And finally, in the 1800s, John Dalton came along and kind of stirred that idea back up. But we're going to start talking about the modern idea and understanding.
Yeah, so historically, John Dalton basically came with the idea that atoms are tiny, tiny little spheres.
Yep.
Okay, of differing sizes. You might have a small spheres and big spheres. So they're just basically different size spheres. So
and he said they're small and indivisible. There's nothing smaller than an atom was his contention here.
Right. So,
and he had a few other things that go into his atomic theory that we've talked about in previous chapters, but we just wanted to remind you, he said atoms are tiny, indivisible spheres. There's nothing smaller than an atom.
Well, the second dude to come around was J.J. Thomson.
Mm.
Who's John? What is this person?
I don't know.
J.J.
J.J.
And J.J. Thomson had a weird idea. He actually discovered something called the electron. Now, you're going to do a demonstration in class.
You're basically going to repeat Thomson's experiment.
Yeah.
We're going to do this all together.
It's called a cathode ray tube.
Right, and so he basically said, okay, I'm going to test Dalton's idea that there's nothing smaller than an atom. And so he put a bunch of atoms of a particular element, probably a gas, into something called a cathode ray tube. So if you want to know what a cathode ray tube, think big computer monitor, not like the flat screen ones, the big ones, or a big TV. Those are all actually cathode ray tubes. They work the same way of his primitive little thing, and you'll see the one we have in lab when you get to class. But he put a gas in there and he ran electricity through it. And then he got out some magnets. And you're going to get to do this. We'll move the little beam of electrons with magnets. And from these moving magnets, he was able to deduce that there was something in there that was negatively charged. And he said, that's kind of weird, because Dalton said that there's nothing smaller than an atom, and these atoms don't have a charge, and yet I have nothing but atoms in here, and there's something with a charge. So he said, that must mean that there's something charged in an atom, something negatively charged in an atom.
This is like the spherical chocolate chip cookie model, I think.
That's right. He came up with the idea that he called the plum pudding model, but we Americans don't eat plum pudding. At least I don't, my family. I don't know what plum pudding is. It sounds kind of gross, actually, but I like to call this the chocolate chip cookie dough model. He says, okay, these electrons are like chocolate chips inside a positive cloud of cookie dough. And that's the chocolate chip version. He said the little electrons are, I think, raisins in plum pudding. Why would you call it plum pudding if there's raisins? I don't know. But he said that the electrons are like raisins suspended in whatever the rest of plum pudding is. And that would be positive. So negatively charged particles in a cloud of positiveness.
And the cloud of the positiveness, folks, is the chocolate chip cookie dough,
right?
Not the chips. And it would have a net positive.
So this is his model. So he took what Dalton said, that they're tiny spheres that are indivisible, and he said, well, yeah, they're tiny spheres, but they're tiny spheres of positiveness that have little negatively charged particles in them. And that is what we call the Thomson model of the electron.
Moving on, we get Mr. Rutherford.
Yep.
Rutherford. Ernie. I have an Uncle Ernie.
Do you? Yeah. I've met Uncle Ernie in Washington.
You did meet Uncle Ernie, that's right.
Yeah. I have a story about Ernest Rutherford. It's really fast. My physics professor in college had a poster of Ernest Rutherford on the wall, and he looked just like Cliff Clavin from Cheers. And so I put a little label over it that said Cliff Clavin on it, and he blew his top. He blew a gasket. It was not the wise thing to do.
So anyways, he discovered the nucleus. What he did is he shot some particles at the nucleus.
Yeah, the particles are called alpha particles, and alpha particles are basically positively charged helium nuclei.
Yeah.
So the important thing is that they have a positive charge. and that they have some mass, and then he fired them through a piece of gold foil. This is called the gold foil experiment.
Very famous experiment.
Yeah. Do we have a picture of that on the next slide, perhaps?
I think so.
Maybe. No,
No.
we don't.
No. So
That's all right. We talked about him back in Unit 2. This
Yeah,
is just trying to
this is
jog
really
your
good.
memory.
Okay.
He fired the alpha particles through the atoms. And he said, well, if Thomson's model is right, they're all going to pass through the atom. Okay? But what happened is most of them passed through, but some of them got deflected. He said, that's weird. Why would they get deflected if
You know what
they're
he said
passing
when he
through?
was down? He says, as if I shot a cannonball at a piece of tissue paper,
Yeah.
and it came back and hit me in the face.
Yep.
That's what he said.
So that's weird, because if it's mostly empty space, then these particles should just go right through. But some of them bounced back. So from that, he was able to conclude that there's something very small, yet very dense, and positively charged
It's called the nucleus.
in the atom, and he called it the nucleus.
In fact, you know how dense the nucleus is?
Very.
Very dense. Most dense substance in the universe. Yeah. It's like, all right, all right, everybody, take your fingernail. Okay, the width of your fingernail, fill the box.
A box the width of my finger.
The
Okay.
box, the width of your fingernail. It's
Oh, not
one
the
fingernail
thickness.
width
Got it,
by
okay.
one fingernail width by one fingernail width.
Okay.
Got that?
So like 1 cubic centimeter-ish?
That's 1 cubic centimeter.
Okay.
And I want you to go grab like a Honda Accord in the parking lot
Okay.
and put it in there. Stuff it in there. But that's still not
You
enough.
can have like 15 clowns in it too.
Sure.
You can get out.
You need 2,000 Honda Accords in 1 cubic centimeter, and that's the density of the nucleus.
Wow. That's
Yeah.
impressive.
Yeah, it's very small, very dense.
So very tiny, very dense, very much positive in the middle of the thing. So most of them did go through like he predicted, but some deflected and some came back.
That's right.
So he said very dense positive nucleus inside, and we have a duplicate.
We have a nice picture twice. Okay.
All right, so wait, let's review. Dalton, small spheres, indivisible.
Oh,
Thomson
okay.
said there's something negative in there, and then Rutherford came along and said there's these negative things that Thomson called electrons, but there's also this positive thing in the middle that I'm going to call a nucleus.
Okay.
Okay.
Now the next guy, I like his name,
Niles.
Niles Bohr. Is he boring?
I doubt it.
I don't know. Niles? I was Niels.
I don't know.
All right. Niels Bohr. He basically answered the big question of where is the electron.
Yeah.
But actually, he got it wrong. But that's another
Yeah.
point. But he tried to figure out where the electrons are. And he said the electrons exist in shells that he called orbitals, because he envisioned the electrons moving around the atom like planets around the sun.
Right. So.
Cool. Well, it's kind of like this thing going around the sun here. See, it's like rotating.
Yep.
So that works pretty well, doesn't it?
Yep. So it has a fixed path moving in a circle. So if you've ever watched The Simpsons, on the side of the nuclear tower, there's that the quintessential typical atom that you see with the nucleus, and then these little things spinning around in these orbits, I guess you could say. Yeah, like that. That's what everyone thinks of like an atom, but the electrons don't do that, but that's kind of based on the Bohr model, that they're on this fixed path like a planet moving around the sun. All right, so he was close. He said that the electron can only be in one particular spot or in another particular spot, but not in between. Then we went one step further from that. And then one step further from that is called the quantum mechanical model, and we're going to tell you all about that in 8.2.
In the next podcast. So that ends the podcast. We'll see you guys in class. Goodbye.